More than 40 years ago, steelworkers seemed to hang this bridge from the clouds, giving all this steel and concrete an almost weightless look. This is the Angus L Macdonald Bridge, a suspension bridge across Halifax Harbour in Nova Scotia. Locals affectionately call it the Old Bridge. But when it was completed in 1955, there was nothing old about it. The Macdonald Bridge was one of the first of its kind in Canada, the longest suspension bridge east of the Rocky Mountains. For 40 years, the Macdonald Bridge helped this region of Nova Scotia grow and prosper. Now the Old Bridge is about to undergo a drastic change that won't be easy. It's about to become the new Old Bridge. The Angus L Macdonald Bridge was not the first bridge across Halifax Harbour. Canadian National Railway built a bridge in 1884. It was a steel swinging drawbridge that was 40 feet wide and a quarter of a mile long. On September 7, 1891, a severe storm blew it down. The second bridge was built in 1892. It lasted hardly a year. There was no storm this time, no roaring wind. The bridge simply collapsed on a calm July night. The builders had tried to drive bridge pilings into solid bedrock. It was not until after World War II that plans were laid for building a third harbour bridge. Angus L Macdonald was the man who recognized the need for it. Post-war Halifax was growing, and harbour ferries could not handle the increase in traffic. Returning veterans from the war wanted the good life that they had dreamed about when they were slogging through mud in Europe or sailing the raging North Atlantic in supply convoys. They wanted a good job, a home of their own, and an automobile. For the generation still shaken by the Great Depression and the Second World War, the Angus L Macdonald Bridge was to become a symbol of hope, a sign in the sky that they could span the tragedy and destruction of the past 2 decades and build a secure and prosperous future. But building the bridge would not be easy. And before it was finished, the Angus L Macdonald Bridge would cost 6 men their lives.
Here we go.
For this man, Hugh Prattley, the Macdonald Bridge was to become the highlight of his building career. He engineered the Angus L Macdonald Bridge.
Well, I guess it's only natural to feel a good deal of pride. I have the unusual privilege of making a pretty big mark on the landscape in my business.
The foundation was first. 2 massive concrete blocks, each weighing 20,000 tons, anchored the bridge on both sides.
And in the case of a suspension bridge, the massive anchorages for the cables, which are sort of like icebergs. You don't see half of the mass of the anchorage when you look at them now, because half of it at least is underground. So they are very massive indeed to resist a very heavy pull.
People stood in awe to watch steel beams flung out over the water and then set in place and riveted. One span after the next extended from both sides at once. They were like arms reaching out for a handshake.
So the bridge suddenly sprouted in 1954. By the late summer, we had the towers up and started putting the cables up. And that took about 3 weeks to put the cables in place. And then we started putting up the trusses, and the bridge took shape in about 6 weeks.
Two main towers, each 300 feet tall, were strung with 72 miles of steel strands squeezed into these steel cables. Each cable contained 61 strands. The towers and piers carry the dead load of 75,000 tons of concrete and 8,200 tons of steel. Yet for all that weight, the Macdonald Bridge seems suspended in the wind as it stretches nearly a mile from shore to shore. Hugh Prattley was on site the whole time of its building. He was even up here with the ironworkers. For him, this was the top of the world. From ground level, it looked as though these men were riding girders and trusses across the sky. They were iron men who pulled muscle from bone with the climbing and scaling to the tops of these towers. They were tough, and they were fearless. On July 3rd, 1954, a random wind caught one of them and threw him to his death 200 feet below. His name was Jean-Marie Boulanger.
But I actually witnessed one man hanging on for dear life because the catwalk was twisting badly, and eventually it threw him off. He couldn't hold on, and I saw him fall right into the harbor. It was a terrible experience for me to witness that. Of course, he was killed instantly, unfortunately, but it was best for him that it was instantaneous, I guess.
By the time the steel grid deck was set in place, 5 more men would lose their lives in building this bridge. On April 2nd, 1955, the Angus L Macdonald Bridge was officially opened. Almost at once, the Macdonald Bridge proved its financial worth.
The estimate was we would get up to 1 million vehicles per annum by about the 3rd or 4th year. In fact, we had 2.5 million the first year.
Over the next 40 years, the bridge became an old friend to both Halifax and Dartmouth. Often, it was the focal point for civic celebrations. Each day for 40 years, thousands and thousands of cars beat the pavement down to the steel decking. Time and the weather have worn the shine off the old bridge. During an annual inspection, the engineering firm O'Halloran Campbell determined that rust and corrosion have made the bridge a little frail and much in need of rejuvenation. The approach decks needed replacement.
So I began to think, well, if we're going to mess up the traffic, so to speak, by tearing up the approach decks and taking a year and a half or whatever length of time to complete the replacement of the approach decks, maybe we should do the 3rd lane because it had been talked about for years.
The engineers determined there would be cost savings and time savings in expanding deck replacement into a 3rd lane project, which included the addition of a bikeway and a sidewalk. The engineering began in January 1996.
And it'll actually be pre-surfaced.
There certainly were challenges on the 3rd lane project. One of the big challenges was how do we accommodate 3 lanes of traffic on the bridge from the old 2. That involves changes in loading.
Load on a bridge is calculated as dead load and live load. Dead load is the load of the bridge itself, the concrete and steel. Live load is the traffic crossing the bridge. Together, they make up the total load the bridge was designed to carry. O'Halloran Campbell had developed and engineered the method for adding an extra lane of traffic, as well as adding a bikeway and sidewalk without increasing the total load on the bridge. It sounds almost impossible.
Now, in the case of this project, we had 3 advantages playing in our favor. The first was that when the bridge was designed in the early 1950s, it was designed for the normal mix of truck traffic. More recently, the approach roads, both on the Halifax side and the Dartmouth side to the Macdonald Bridge, were no longer designated truck routes, so the bridge was not used for normal large trucks.
No trucks means that the bridge carries a lot less live load than it was designed to carry.
The second item in our favor was that whereas the Macdonald Bridge was designed to take a 30-inch diameter water main, when the water main was installed, which was in 1971, it was installed as a 24-inch water main, so it meant that the load from the water main was less than it had been designed to be.
In very simple terms, the engineers traded the calculated weight of truck traffic on the bridge and water through the water main for the extra weight of the third lane, as well as the bikeway and sidewalk. A third advantage playing into the project's favor was the engineers' decision to use a lightweight epoxy wearing surface instead of the 1-inch heavier asphalt.
Had we not been able to use those lightweight wearing surfaces, and for instance, had we had to accommodate truck traffic, then we would not have been able to move forward with the third lane project.
Diaphragm plate here.
Another factor was the use of a lightweight construction material called an orthotropic steel plate.
Steel plate deck and the supporting structure.
In simple terms, it's a near horizontal steel plate, which is about a ½ an inch thick, and it has stiffening ribs running underneath it in the direction longitudinal to the bridge, that is, with the direction of traffic.
The orthotropic steel plate allowed the engineers to design deck replacement one panel at a time. This new lightweight orthotropic steel plate would be used in the roadway area on the approach spans and on the sidewalk and bikeway. The next engineering challenge was this: where to put the third lane of traffic and where to put the bikeway and sidewalk. On a suspension bridge, the width between the stiffening trusses is fixed. To the average eye, there just isn't enough room to accommodate a third lane. O'Halloran and Campbell, however, did not see it that way. What they saw was the width between the stiffening trusses accommodated 2 lanes of traffic, plus a sidewalk and ductway for utility cables. The sidewalk and ductway each measured about 1.5 meters wide.
We were able to take all of those cables and put them underneath the deck of the bridge in a specially made cableway. By taking the south sidewalk and converting it to a cantilevered structure outside the main truss, and doing an exactly similar thing on the north side with the bikeway, we were able to open up the available width inside the trusses.
Cantilevering the bikeway and sidewalk from the bridge structure provided the next big challenge. It all may look good in a computer graphic, but how well will the bridge and these extensions endure the high winds that blow down Halifax Harbor?
The bridge, of course, has been standing there at that time for 40 years and had survived a few hurricanes, and so we knew it was pretty solid, but we didn't know what the sidewalk and the bikeway would do to the wind resistance.
Come on down.
It was necessary to do aerodynamic modeling, and it was found, interestingly, that the performance of the bridge was better if we had symmetrical cantilevered structures. So that meant the sidewalk and the bikeway could both go ahead as proposed, and they would each balance the other and give better aerodynamics.
Turned out to be a safety factor. We had actually improved the safety of the bridge.
The engineers were not the only ones with challenges to overcome. The joint venture of Walter Construction and Cherubini Metalworks had a significant challenge of their own. They had to renovate the old bridge within very strict time constraints.
The most difficult was the replacement of the approach span roadway decks. We had to take off the old existing reinforced concrete deck and replace it with a new steel orthotropic deck panel. Those replacements had to be carried out overnight between 7 p.m. and 5:30 a.m., which was the only time at which we could close the bridge to traffic. Getting those panels fabricated and in place through those time periods was a significant challenge.
To meet both the daily and project completion deadlines, Cherubini had to pre-assemble all replacement sections at their Dartmouth location. Cherubini welded 17 steel plates into a single unit that measures 40 by 17 feet.
The ribs were fabricated, again, from flat steel plates. They were cut out on a plasma machine to cut to the profile of the rib plate.
A plasma burning table is like a cookie cutter for steel plate. The steel plate is submerged in a water tank to reduce heat input and thereby reduce distortion in the plate. A bending machine bends the rib profile into the desired shape. Using a traversal welding machine, Cherubini attached the ribs to the deck plate, which is equal in width to 3 lanes of traffic.
The sidewalk and bikeway panels were also fabricated in our Dartmouth plant, and they were trial assembled to each section of the bridge as we progressed through the work.
That allowed us several advantages. It mitigated the risks of weather. It also allowed us some schedule advantages because those could be built off in the shop while we were doing other things out on the bridge.
Walter Construction also designed special scaffolding to give their workers safe, unrestricted access to the underside of the bridge. The overnight installation of the deck panels required the logistics and clockwork of a military engagement.
We developed a schedule for the overnight operations basically on 15-minute intervals. We would go out with big electric saws and core drilling machines, and we would cut the bridge into 2 panels, 10 feet long. The width of the bridge, which was effectively 40 feet. And we would do that the night before they were to be removed. And we would also core drill those panels with holes so that we could put a steel plate over them the next day and bolt them down and hold them in place.
Walter Construction also designed a specific type of crane for lifting out the old decking and lowering the new. It's called a straddle carrier. Each night, they rolled the straddle carrier onto the bridge and lifted out the old decking.
And we would do that for both panels, and then that would leave us the access to bring in the new orthotropic steel panel and drop it in place.
The engineers are on site full-time to make sure each panel fits within acceptable tolerances.
Put it on the first one and we'll check it.
We had to be within basically 1/8 of an inch in a running dimension at any given time. And there was other considerations as well. We wanted to keep going in a straight line because if you start deviating off our intended line by even 1/4 of an inch, by the time you jump up a number of panels, the bridge would start to run off in the wrong direction, and we didn't want that to happen.
To remain on schedule, the joint venture had to install 1 deck panel per night. Installation of the orthotropic panels required a welding procedure that had to be done under controlled conditions. The Angus L Macdonald Bridge is hardly a controlled environment.
If not rain, the high winds would have made it difficult to do the welding. So in order to overcome this, we designed an enclosure, which we referred to as the igloo. It was an aluminum frame covered with plastic, 10 feet by 40 feet long, and we rolled it into place, closed it over the joint, sealed it up, and the tradesmen worked inside that. 4 crews of welders worked simultaneously to get the weld done in time to get the bridge open.
Another panel, another night, and another race against the clock to complete the work and have the bridge opened at 5:30 a.m. for rush hour traffic. The installation of 128 orthotropic panels was on schedule. In September 1999, the work was done, 2 months ahead of schedule.
In hindsight, it didn't seem all that bad, but now at the time it was a very aggressive and very tight schedule. But we pulled it off.
The end of the job.
Most of the people with Walter Construction are local people, and in that this is a major project locally. We're very proud of our role.
It is a big advantage in terms of an improved link across the harbour. So yes, we're proud of it, and we're very pleased to have been associated throughout the length of the project.
We put a deadline of November '99 on them for completion, and they not only met that deadline, they exceeded it.
On October 31st, 1999, the new Old Bridge was officially reopened. In 1955, one generation built this bridge as a promise to the next, that this region of Nova Scotia would prosper and grow. With the addition of the third lane, a similar promise has been made to those generations that will follow. And this partnership of engineers, contractors, steel fabricators, and bridge commissioners has ensured that our new Old Bridge keeps that promise well into this 21st century.